Section 13.2. Logarithms. Okay, so first let's recall 2 cubed is 8. And so I have here a base of 2, an exponent of 3, and I have my result of 8. Well, I can write this as follows. I can just say the base is 2, the exponent is 3, and the result is 8. And so since 2 cubed is 8, then the log base 2 of 8 is 3. So the logarithm is an exponent. Okay. Let's just see. Okay. Well, this is crashed. Okay. Let's see if I can do anything. Oh, wait. That moved. Okay, let's see if I can. So this is going. Okay. Let's see if I can get a new window. I can do something on that window. Okay. See if I can do nothing on this window. Okay, so let's just get rid of this. Okay. Okay, so let's draw. Okay, so section 13.2, logarithms. So let's recall 2 cubed is 8. And this exponential form can be written in logarithmic form as the log base 2 of 8 is 3. And so the base here is 2. The exponent is 3. And the result is 8. And so we can rewrite the fact that 2 cubed is 8 as saying that the log base 2 of 8 is the exponent 3. So logarithms are exponents. And so similarly, 3 squared equaling 9, written in exponential form, can be written in logarithmic form as log base 3 of the result 9 is the exponent 2. So note that f of x equaling b to the x, well, if you remember, for bases greater than 0 and not equal to 1, well, if the base were greater than 1, then it's always increasing, so it's an injective function. And if the base is between 0 and 1, then it's always decreasing, so it's yet again injective. And so this is an injective function. And so that means that the exponential function has an inverse function. And we call this inverse function the logarithmic function. So the inverse of the exponential function is the logarithmic function. So let me state that. So the logarithmic function first, suppose that your base is greater than 0 and not equal to 1. Then the logarithmic function let's call it g of x, the log base b of x. This is the inverse function of the exponential function. Let's call it f of x equals b to the x. So notice that the base b here is the same. Okay. So this base b is the same as that base b. Okay, let's look at the graph of the exponential function. So the graph of the exponential function looks something like this. The logarithmic function looks something like this. So this is the graph of y equaling log base b of x for the case that b is between 0 and 1. Okay, So note that this is always decreasing. Maybe I'll put it over here. So always decreasing. So it's always decreasing here. Okay. It is concave up. It's decreasing, but it's at a increasing rate, so it's always becoming closer and closer to zero slope. It has no horizontal asymptote. But it does have a vertical asymptote. It goes straight up. So it has a vertical asymptote. The vertical asymptote is x equals 0. So the y-axis. No x-intercept. No y-intercept. The x-intercept is at the point 0, 1, which corresponds to, if you look at the graph of the exponential function, it's just, well, the y-intercept for the exponential function. Okay. Okay. Let's look at the graph of the logarithmic function. Oh, and I guess I should note the domain. The domain it goes from 0 to infinity. So this is not defined for values of x equal to 0 or less than 0. The range is all real numbers. Okay. Let's look at the graph of y equal log. Base b of x for b greater than 1. If I do that, actually let me bring this down. Maybe I'll bring it down here. So if I look here, let's go a little further down so I can do it. Something like this. Okay, so it is always increasing. It's concave down. It's increasing but at a decreasing rate. It has no horizontal asymptote. The vertical asymptote is x equals 0. Oh, but you notice for here, y approaches positive infinity. But here, y approaches negative infinity. Okay. No y-intercept. The x-intercept is the same. 0, 1. The domain is the same. You can't have negative x values nor x equaling 0. And the range is the same. It's everything. Negative infinity to infinity. Okay. Good. Let me give you some notation and terminology, really. The common logarithm. So when these logarithms were invented, it was because they were trying to do calculations, and our calculations, our number system has a base 10. And so the logarithms all had a base of 10, so they just used the notation log 10. So if you don't see a subscript, a base here, then the base is understood to be a base 10. Lately, especially since the advent of personal handheld calculators, we use what is called the the natural logarithm, which is the log, but the base here is that number e that we just introduced from the previous section. Okay. So let me do some examples on page 549. Oops. Let me do problem number 1. In exercises 1 through 20, rewrite the logarithmic statement as an exponential statement. So we're going to go from logarithmic form to exponential form. So the log of 100 equals 2. Okay, so now let's rewrite this in exponential form. Well, the base isn't written, so it's a common logarithm. So the base is understood to be 10. The exponent is your logarithm, and the result is, well, what was given in the logarithm, 100. Let me do problem number 3. Log base 2 of 8 is 3. So the base is 2, exponent is 3, result is 8. Let me do problem number 5. Log base 5, 25 equals 2. So the base is 5, exponent is 2, result is 25. Let me do problem number 7. log 1 over 100 equals -2. Base is 10, exponent -2, result 1 over 100. 9. Log base 5, 1 over 125 equals -3. Base is 5, exponent -3, result 1 over 125. 11. Log base 16 of 4 is 1/2. And so the base is 16, exponent is 1/2, result is 4. To problem 13. Log base 100 of 10 is 1/2. So the base is 100. The exponent is 1/2. And the result is 10. So that is the same as the above statement written in exponential form. 15. ln e to the 2 is equal to 2. So the base is e, because we have the natural logarithm, so it's assumed to have base e. The exponent is 2, and the result is e squared. 17. Log a b equals c. So the base is a, the exponent is c, and the result is b. 19. ln e squared equals d. So the base is e, the exponent is d, the result is e squared. 21. In exercises 21 through 35, rewrite the exponential statement as a logarithmic statement. So 2 cubed is 8. That can be written as the log base 2 of the result 8 is equal to the exponent 3. 23. 3 to the -2 is 1 over 9. So this can be written in logarithmic form. The log base 3 of the result, 1 over 9, is the exponent negative 2. So the log base 3 of 1/9 is negative 2. 25. 10, negative 1, 0.1. And so the base is 10. The result 0.1 and the exponent negative 1. Since I have a base of 10, I can just use the common base notation, the common logarithm notation, and just not write the base. And it'll be understood to be 10. 27, 5 to the x equals 8. So this can be written in logarithmic form. The log base 5 of the result 8 is the exponent x. 29. 6 squared is 36. So this can be written in exponential form as the log base 6 of the result 36 is the exponent 2. So we can think of this as saying the log base 6 of 36 is 2 because 2 is the exponent of 6 that yields the result 36. 31. A to the power b equals c. And so this is the same as the log base a of the result c is the exponent b. 33. The square root of 3 is 3 to the 1/2. So this can be written in logarithmic form as the base is 3, the result is rad 3, and the exponent is 1/2. Let me do 35. The fourth root of 16 is 2. So I can write this in logarithmic form. The base is 16. The result is the fourth. Actually, let me just write this fourth root as 16 to the 1/4. So just recall that that 16 to the 1/4, when we're doing rational exponents, is the same as the fourth root of 16. And so now let me write this in exponential form, in logarithmic form. And so this is the same as the log base, well, the base is 16, of the result 2 equals the exponent 1/4. 37. G of x equals log base 4 of x. Okay, well, in exercises 36 to 50, sketch the graph of the function. So let's do that. The base is greater than 1, so it looks something like this. This is the graph of y equaling log base 4 of x. Give the coordinates of the x-intercept. The x-intercept is at 1, 0. The log base 4 of 1 is 0. The exponent of 4 that yields the value 1 is 0. The equation of the asymptote, well, the asymptote is just x equaling 0. 39. G of x equals the log of 1/2 x. So let's sketch the graph of this. So again, it looks like the inverse function of 1/2 to the x. So it looks something like this. So this is a graph of y equals a log base 1/2 of x. The x-intercept is at 1, 0. And the asymptote is just x equals 0. 41. F of x equals log base 5 of x. Well, it's going to look almost identical to 37. It'll just be a little steeper, that's all. So this is a graph of y equaling log base 5 of x. Well, the x-intercept is at 1, 0, and the asymptote, vertical asymptote, is x equaling 0. (43) F of x equaling the log base 3 of x minus 1. Okay, so let's do that. Actually, let me find the asymptote first, the vertical asymptote. Vertical asymptote will be found by setting what's inside the logarithm to 0. So x equaling 1 is the vertical asymptote. The x-intercept can be found by setting what's inside the logarithm to 1. So that says x equals 2, and so the x-intercept is at 0, 2. Let's make that a little straighter. So let's draw this. It's quite a bit off. Okay, good enough. And so it looks like the log base 3, which looks like that. Looks like almost all these. Yeah, so it looks like 37, 30, 41. It's very similar to this, except that we translated this over. So let's have the vertical asymptote here at x equaling 1. Then it looks something like this. So this is the graph of y equaling log base 3 of x minus 1. So at 2, it's 0. At 4, it's 1. At 10, it's 2. Okay, 45. F of x log base 3 x plus 2. Okay, let's find the vertical asymptote. Set x plus 2 equal to 0. So the vertical asymptote has the form, oh, and maybe I should actually box that. So the vertical asymptote has the equation x equaling negative 2. Let's find the x-intercept. We can find the x-intercept by setting what's inside the logarithm to 1, subtracting 2 for both sides, you get negative 2. Okay, so let's sketch the graph of this. So it should look similar to what we graphed in the previous sketch. So it'll have the same basic shape. It'll just be translated over differently. So we're going to translate 2 to the left. So this is x equaling negative 2. And so it should look something like this. This is a graph of y equaling log base 3 of x plus 2. So I have, it intersects here at negative 1, 0. At 1, it's 1. So at 1, it's 1. At 7, it's 2. 47. F of x equals log base 3 plus 1. Okay. 1 plus log base 3. Okay. So the vertical asymptote is just x equals 0. Setting that to 0. The x-intercept. Ooh. Well, the way you find the x-intercept is you set y to 0 and solve for x. And so the log base 3 of x is -1. Let me write this in exponential form. And so the base is 3, exponent is -1, and the result is x. And so that says the x-intercept is at 3 to the -1, which is 1/3. Zero. Okay. So let's do this. So again, it should look the same as the previous ones. But we have translated this up by 1. Which is going to look a heck of a lot different. Okay, so I've just taken this guy and moved it up by 1. Okay, so good enough. Okay, so this is the graph of y equaling 1 plus log base 3 of x. So the asymptote, vertical asymptote is x equals 0. The intercept, x-intercept is at 1/3 0. Okay. 49. F of x equals 1 plus log base 3. So again, it'll look similar to what we've drawn before of x plus 3. So let's find the vertical asymptote. Set what's inside the logarithm to 0. So the equation of the vertical asymptote is x equal -3. Let's find the x-intercept. And so let's set y to 0 and solve for x. Subtract 1 from both sides of your equation. So the log of base 3 of x plus 3 is -1. Rewrite this in exponential form. And so the base is 3, exponent is -1, and the result is x plus 3. Subtract 3 from both sides of your equation. And so I have 1/3 minus 3. And so the x-intercept is at 1/3 minus 9/3 and -8/3, 0. So let's sketch the graph of this. And so the vertical asymptote, I'm going to shift this to the left 3 and up 1 of the graph of log base 3 of x. And so it should look something like this. So y equals 1 plus log base 3 of x plus 3. So the x-intercept is at negative 8/3, 0. Okay, and so that finishes off section 13.2.